Hi everyone, today we're going to learn about inverse relations and functions, so let's get started. First thing that we're going to talk about is what are one-to-one functions. And a one-to-one function is basically any two elements of the domain corresponding to the same element in the range. You cannot have any repeated y values. So for something to be one-to-one, it would need to look like for every one value of x, you have a value of y, but you can't have another value of y for you to have a function that is one-to-one. So for a function to be one-to-one, you can't have more than one repeated y value. Whereas this function, you have Indiana, population 6.4 million. Each one of these has one value for y. Whereas if you look here, so this would be yes, one-to-one. Where this one, I have dogs and cats, both have a life expectancy of 11. That would be not a one-to-one function. Which one of these are one-to-one? When you're looking at these equations, or these functions here, you've got for every value of x, you have a y value. That these are all different, so this would be one-to-one. Here you have this value of x to y and this another value of x to y. This would be not one-to-one. This one right here, you have a value of x, has a y value, a value of x has a different y value, and a value of x has a y value. So if you were to graph that, here's x and here's y, here's x, here's y, and here's x and here's y. So if you say, is that one-to-one? Well, that is going to be one-to-one. It may not be a function, but this is one-to-one. This one right here, you have two values for y here. You would say not one-to-one. There's another way of determining if something is one-to-one. And you would say if it passes the horizontal line test. So meaning if I were to draw a horizontal line straight across, and it actually intersects in more than one place, this tells me it's not a one-to-one function. Obviously, because if you went to the left, so let's say -1, you have this value, and +1, here's the value here. Whereas in this case, if I use my horizontal line test, I'm only intersecting once and not twice. So therefore, this is one-to-one. Horizontal line test for this equation, not one-to-one. Here, horizontal line test, this would work because remember, that has an asymptote right across from here, right going through here. So this is one-to-one. All right. Now, an inverse relation is interchanging the coordinates of each ordered pair in a relation. So basically, if I have a point, let's say I have the point 2, 3, okay? And I asked you for the inverse of that. All I'm asking you to do is to flip your x and your y values. And so now my point is going to be 3, 2. Another way of looking at that, okay, is drawing a graph. Let's see. If I were drawing a graph and I had the point, let's say I had the point 6, 1. So here's 6, here's 1, here's 0.61. And I wanted to find the inverse of 6, 1. All I have to do is take 6 and 1 and I have to flip those apart. So that's going to be, my new point is going to be 1, 6. And so that's going to be here 1, 6. Now those are inverses of each other. Now another pretty cool way of figuring out if these are inverses is if they are reflections across the y equals x axis. So this is y equals x. And if you notice, these are going to be reflections. For example, if I said 0, -3. So here's my point, 0, -3. Remember, take your x and y and flip it, and now I have -3, 0. There's -3, 0. See how this is a reflection across here? That's a reflection across here. So that is, anytime you have an inverse relation, it's a reflection across the y equals x-axis. These right here, this is a parabola, x squared minus 5x. Know that, let's try to graph this. Let's plot some points here. We can factor out an x. We have x minus 5. That's going to give us 2x intercepts, x equals 0 and x equals 5. So we have a point here and we have a point here. And so not completing the square or finding the vertex down here, which I could find. I could use my shortcut method, which is negative b over 2a, and then plug that in, negative b over 2a. I could definitely do that, but that's not the point here. What I'm trying to do is to show the inverse by reflecting across the y equals x-axis, meaning if I were to draw in my y equals x-axis like this, okay, that's y equals x, my graph flipped over would probably look like that. It would, and I could plot some points. So this is 5, 0. This is 0, 0. That's not helpful. But let's just say this is, I don't know, 2, negative 3. So if that was 2, negative 3, then negative 3, 2 would be here. 5, 0, 0, 5 would be here. And guess, this would look like that. So does that look like a reflection across the y equals x-axis? Absolutely. And in fact, what this does here is this gives me this value like this, okay? And that's what that is. So this right here, do you notice anything about these graphs? What you should say is that you should notice that there is a reflection across y equals x-axis. So there's your y equals x. Okay. So again, given points, points are easy. To find the inverse given just points, you just take the points and you switch them out. So for this point right here, negative 2, 6, the inverse of that would be 6, negative 2. For this one right here, 0, negative 3, the inverse would be negative 3, 0. For this right here, negative 6, 2, the inverse would be 2, negative 6. So I'm going to plot those points. So I have 6, negative 2, 2, 3, 4, 5, 6, negative 2. Let me use a different color. So we have 6, negative 2. 2, 1, 2, 3, 4, 5, 6. And then we have negative 3, 0. So what you have is this, and then this. And then again, it's a reflection across your y equals x-axis because you have this line that cuts it in half, and it's a reflection right across that line. That's an inverse function. It's an inverse. Something to remember, and because we're going to be talking about inverses a lot, that says F inverse. You can also write Y inverse, but this says F inverse, and you notice that this negative sign here, that is not an exponent. I know from algebra, a lot of people learned this. So let's say I had 1 over x squared, and I rewrote that, and that could be rewritten as x to the negative 2 power. Or I could write 1 over a, and that would be a to the negative 1 power. This is not that. This is not an exponent. So when I'm using this f to the negative 1, it's not an inverse, okay? Excuse me, it is an inverse. It's not an exponent. So we're going to start finding inverses other than graphing. So we can graph. You can definitely graph. That's the first way to find an inverse, is to graph and to flip, to reflect your picture, your equation or your function across the y equals x-axis. We're not going to do that. We are actually going to solve it algebraically. And in doing that, there's some steps to doing that, to solving, finding an inverse algebraically. So the first step is you replace your f of x with y. So we're going to replace that with y. So we have 4 over x plus 7. And then the second step is to interchange the x and the y. So we have x now is equal to 4 over y plus 7. The last or the next step is to solve for y. So in order to solve for y, I'm actually going to cross multiply. And so 4 times 1, that's 4, is equal to x times y plus 7. And I'm going to distribute. So I have 4 equals xy plus 7x. And I'm still trying to solve for y. So I'm going to move the 7x to the other side. So I have xy equals 4 minus 7x. And I'm going to divide by x. Now I have my y by itself. So I have y inverse is equal to 4 minus 7x divided by x. And so there's my inverse. Now, there's actually some pretty cool things to learn about inverses. And number one, from the original equation, which is right here, and then we switched our x and y and we solved for y. Something to remember is that when you are when you have a function, so like if I were to graph this function like this, I would have an asymptote at -7. So here's -7, let's say. Here's my asymptote. It looks like I have another asymptote, horizontal asymptote at y equals 0 because it is bottom heavy. And my graph probably is going to look something like this. I'm going to graph x's, or excuse me, when I'm going to find the intercept. So if x went to 0, y would be 0, 4 sevenths. So that would be up here. So it looks like my graph is going to do this and this. And what that would give me is a domain. Remember, my domain goes on my x-axis. It's low to high. And so that's going to be in -infinity to -7. So that'll be -infinity to -7 union, and then -7 on. So that'll be -7 to infinity. Okay? And my range for this function is going to be low to high. So it's going to be -infinity to 0, because remember, that's where I have an asymptote right here, union 0 to infinity, because it's going to go up. The unique thing about finding the inverse, which there's my inverse, okay, is that not only is this graph going to be reflected across my y equals x axis, so that will look a little bit different, right? It'll look probably, let's see if I can use yellow. There's something like that, and then something like that. That's what it's going to look like. But the really cool thing about this is that my domain and range for my inverse actually is flipped from my domain and range for my original function. So I don't even need to figure anything out, because my new domain for my inverse function is actually my range for the function. So my domain, so this range is my domain. So I would say -infinity to 0, union 0 to infinity, and my range is now my domain. So that would be, -infinity to -7, union -7 to infinity. Okay, so finding the inverse, let's do that. So, and let's just graph it first, okay? This shows me that I have a vertical asymptote at 3, and 2, 3. And if you watched all the videos from the previous chapter, which was on polynomials, rational equations, etc., lots and lots of material, you know that the vertical asymptote comes from here, and this is going to give me my x-intercept. And then also looking at x over x, that's going to give me my horizontal asymptote, which is at y equals 1. And then I have an x-intercept at -4, 0. So, and then I have a y-intercept at, set x equal to 0, -4 thirds. So it kind of looks like my graph does something like this, and then like this. Okay, cool. So for that, I'm going to find the inverse using algebra. I'm going to find it algebraically. And so in doing that, again, I go y equals x plus 4 over x minus 3. I'm going to switch my x and my y. So now I have x equals y plus 4 over y minus 3. And in order to solve for y, I'm going to cross multiply. So the next thing I'm going to do is multiply. So x times y minus 3 equals 1 times y plus 4. To solve for y, I actually need to get this y out of these parentheses. So I'm going to distribute first. So I have xy minus 3x equals y plus 4. I need to get the y's on the same side. So I have xy minus y equals 3x plus 4. I'm going to factor out a y, and I'm going to get x minus 1 equals 3x plus 4. And I'm going to divide by x minus 1, that whole quantity. And that gives me now y by itself, which is now my inverse. And that's equal to 3x plus 4 over x minus 1. And so that is my inverse. Okay, so again, steps. Steps are change f of x to y. Check, did that. Switch your x and y. Solve for y. So, all right, we did it. Find the inverse. Now, I just want to actually go over the domain and range with you again one more time. The domain for my original equation, if I look at my graph, right, it's going to be from negative infinity to, this is 3, to 3, union 3 to infinity. And my range is going to be low to high. So it's going to be negative infinity to, where's my horizontal asymptote at 1? There it is right there. Union 1 to infinity. And my new range and domain for my inverse function, okay, there's my inverse, is going to be the switched out. So my domain, here's my range. So my domain is my range. So domain is going to be negative infinity to 1, union 1 to infinity. And my range is going to be my domain for the original equation, and that's going to be negative infinity to 3, union 3 to infinity. All right. So back to the horizontal line test. This is kind of important. Again, this is not one-to-one. It's not one-to-one because I have two values for y a lot. You can't graph the function more than once, then the function is not one-to-one, but this is what's important. Therefore, its inverse is not a function. So if you recall, the inverse for a parabola is going to be reflected across the y equals x axis. And what this is going to look like is this. Well, of course that's not a function. It doesn't pass the straight line test. Check, doesn't do that. So there definitely it's not a function. If it's not one-to-one, then its inverse is not a function. So the question for this slide is basically which one of these are one-to-one. This is not, because it doesn't pass the horizontal line test. This is, yes, is one-to-one. No, it's not one-to-one, doesn't pass the horizontal line test. This one does pass the horizontal line test. This is one-to-one. Oops. Properties of functions and inverses. So there are some properties that are pretty important. If a function is one-to-one, then the inverse is a function. We just talked about that. The domain of a one-to-one function is the range. We've talked about that, of the inverse. And the range of a function is the domain of the inverse. And lastly, a function that is increasing or decreasing over its entire domain is one-to-one. So maybe an example of that would have been our last example of something like this, where it's increasing or decreasing over the entire domain. So if I started left and I went up, see how it's still increasing? Okay, so that would be a one-to-one function. So this one right here, we're just trying to check this out and do another problem like this. Again, is this one-to-one? This function, yes, it's one-to-one. Give the domain and range and find the equation for the inverse, and then give the domain and range for the inverse. So again, you would start off with your equation. Oops, And the first thing you would do is switch your x and y. So we have x is equal to 2y plus 3 over y minus 1. I'm going to multiply across. I'm going to come over here, and I'm going to go, that's x times y minus 1 is equal to, and then put a 1 under here. So that's going to be 1 times 2y plus 3. I'm going to distribute. So I've got xy minus x equals 2y plus 3. I'm going to solve for y. So I'm going to move this y over to the other side. So I have xy minus 2y equals x plus 3. I'm going to factor out a y. I'm going to get x minus 2 equals x plus 3. And I'm going to divide by x minus 2, which now gives me my y inverse equals x plus 3 over x minus 2. So here's my inverse. And again, my domain and range, I'm going to find that. But let's graph it first. I really think it's important to graph. And everybody is, after the last chapter, are pretty good. You're a pretty good example of you can do graphs. Here we have x minus 1. So we do have a vertical asymptote at 1. Looking at my HA, or my horizontal asymptote, it looks like I do have a horizontal asymptote at 2. Looking at my y-intercept, it's going to be at -3, so 0, -3. Looking at my x-intercept, I'm going to set this equal to 0, and I'm going to get 2x equals -3, x equals -3 halves, which gives me -1.5, which is here. So that's going to give me a graph that does this, like that, and like this. Oops, not supposed to touch that. All right, so let's move that up. That's pretty cool how I can do that. Okay, so what we have is my domain for this. So my domain is going to be left to right. So it's going to be -infinity to, what's this value? 1 union 1 to infinity. And my range is going to be low to high. So -infinity to 2 union 2 to infinity. Now, I know that we can use the flip, we can reflect across the y equals x axis, but I just want to show you what this graph would look like just by graphing it again by hand. And by doing that, you have a vertical asymptote at 2, you have an x-intercept at -3, 0, and you have a horizontal asymptote at y equals 1. So, and an x-intercept at -3 halves, which is 1.5. So your graph is going to do this. Okay, and this right here. And again, if you drew in, right, if you drew in your y equals x, okay, see how these are going to flip? They're pretty close, actually. See how these are, oops, these are pretty close. Okay, those are pretty close. And so when you reflect those are going to look like each other. So remember, when I'm putting in my domain and range for my new function, it's the range and domain of the other. So my domain for my inverse function is my range, and my range is my domain. Okay? All right. So this is actually pretty important. This slide talks about composition of functions. So what this is another way of finding the inverse, or telling if two equations are inverses of each other. So what I mean is we know that we can graph, right? We can graph, okay, and reflect across the y equals x axis. We can find the inverse algebraically, okay? This method, which is, we call it the composition of functions, basically plugs f of x into the inverse and plugs the inverse into f of x. And if you do this, so like, I don't know if you can see, there's a kind of small, but if I plug the inverse, okay, into my f of x equation, I'm going to get x if it's an inverse. And I could also have an inverse function and plug in f of x and get x. And what that tells me is if I get x, okay, if I do get x, that means yes, it's an inverse. That's the whole point of that, okay? And it's called composition of functions. So let's try that. Okay, so the first thing you're going to do, see, here's f of x, and here's the inverse of f of x. Now, I don't actually have to do that. I mean, I could, right? I could go like this. Y equals 5x plus 8. I could switch out my x and y. X equals 5y plus 8. I could solve for y. I get 5y equals x minus 8. Divide by 5. I get x minus 8 over 5. I have that right here. So I don't have to do this, okay? So what it's saying is you don't have to do that. It's saying here it is. There's the equation. So given that, they're asking you to prove it. So they want you to prove it using the composition of functions. That's what you're doing. So what I want you to do is to plug this equation into the f of x, or the f of the inverse into the f of x. So you're going to go f inverse f. So I'm plugging the f of x equation in for x. So in doing that, I'm going to get 5 times x. I'm going to use a different color to show that. And that's going to be x minus 8 over 5. And then add 8. Okay? Well, 5s are going to cancel. I get x minus 8 plus 8. 8s are going to cancel. X. So f inverse of x is equal to x. Happy face. That's good. That's what we want. We want it to equal x. So now I'm going to prove it the other way, and I'm going to take my f inverse equation. So let me draw a little line here. And I'm going to say, well, I'm going to take my inverse and plug in the f of x equation into that, and hopefully I get x. So there's my f of x, my inverse equation. I'm going to put x right into that. See that right there? 5x plus 8 is going to go right there. So I'm going to go 5x plus 8, right? Minus 8 all over 5. And so my 8s are going to cancel. You have to do the numerator first. So this, simplify the numerator. Those are going to cancel. So I have 5x divided by 5, which is x, which is what I want. And so if you get x here and here, therefore, they are inverses of each other. Okay, cool. So this is just going back to one-to-one equations, one-to-one functions. A function is one-to-one if you plug in, if A does not equal B, then f of A is not going to equal f of B. In addition to that, if you plug in f of A and equals to f of B, then A has to equal B. The outputs are the same, the inputs are the same. So this is if a function is one-to-one. This is just another way of showing that it's one-to-one. So what we're going to do is we're going to practice. So in this problem, I'm going to plug in A and B. So I'm going to say, well, f of A would be 2a minus 3, and f of b would equal 2b minus 3. Well, if it's one-to-one, then I can set these equal to each other, and a should equal b. So 2a minus 3 should equal 2b minus 3. Well, if I add 3 to both sides, I get 2a is equal to 2b. If I divide by 2, I get a equals b. Yes, they're one-to-one. So for me to prove that something is not one-to-one, remember, finding two numbers, a cannot equal b, therefore g of a equals b. If I prove that they're not one-to-one, then they would be the same value. So what we would do is we would plug in, let's say, a number such as -1 and 1. See, A does not equal B. They're not the same. I have a -1 and a 1. And by the way, you can only prove that it's not 1-to-1 if they're quadratics. That's a huge that's really important. So we have 3 times -1 squared is 3 times 1, which is 3. 3 times 1 squared is 3. Well, if I plug in -1 and 1, which they're not the same, but I do get the same answer here, that's telling me they're not 1-to-1. Because if I put in different inputs, I need to get different outputs. But if they're the same, then remember, they're the same y values. If I were graphing that, remember, if -1, 3, +1, 3. If I were to graph that and I were to draw a line using the horizontal line test, not 1-to-1. They have to pass the horizontal line test. This is just another way of showing if something is 1-to-1. So I hope that helps, and I will see you next time. Thanks.